Oh. I should have raised my board before I start the video, but what's the fun in that? So what's my range of motion here? So I can't quite go all the way to the bottom of the board, which I suppose is okay. Also, the blurring in and out is gonna drive me nuts. Videography. Oh boy! So, let's talk about kinematics. So we're just finishing up our discussion on electronic circuits. Power flows, and there's power. And you have all of the important equations, including the power equation, which is voltage times current is equal to power. That's all behind us at this point, meaning that we're still going to have to know it, but we have other stuff to do. This class is kind of a compilation of a number of different classes, including circuits, physics 1, dynamics. For those of you who have already taken fluid mechanics, there is a little bit of fluid mechanics, a little bit of heat transfer, thermodynamics. It's a little bit of everything. And I'm going to draw some strings and pull everything together at some point. You may start figuring out where the likenesses are. My goal is to blow your mind. So we'll do that, just it'll take a little bit. So here, we're going to go back to dynamics, physics 1, talk about some of the fundamental ideas. Okay? So we've talked about the difference between component equations and system equations. What kind of system equations are we dealing with? Well, when we're talking about 1D linear motion, which is, you have a car, and your car travels. Wow, that is squeaky. I am not an artist. No one has ever accused me of being an artist. But you just have a vehicle traveling like this. You have some accelerations, you have a velocity, you have a displacement. Okay, that's where we're headed in this particular series. So 1D linear motion, that's what it means. Your system equations are going to come down to, it's kind of very interesting, but you have your sum of all forces is equal to 0, okay? On a rigid body, sum of all forces are going to be equal to 0. Now here, included in this, you may be used to, what happens to mass times acceleration? Well, we do have the mass times acceleration. It's kind of built into this, but we'll talk about that at that point. It's called a D'Alembert's force, and so this is not quite what you're used to. It's a vector, having this equal to 0, but in systems and controls terms, this is what we're working with. Again, we'll get into why things are slightly different in this class from what you had in other classes. It's kind of like waking up from a dream and everything that you thought was real is kind of off and you notice it. Well, that is this class. That's pretty much everything about this class. Everything's a little bit off, but suddenly things start clicking. Okay, so this is the system equation. That's it. We have one. And part of that is because in your system equation, we don't really have, we don't have, oh, there's a limit to how many accelerations you can have. Not quite. So let's go into what are the component equations here. Well, in linear motion systems, there are basically 3 different types of major components that we're going to be dealing with in this class. Okay? we have a mass. A mass has a relationship between its own force and its acceleration. So not only do we have the displacement equations that you would have learned in 320 that link displacement, velocity, and acceleration. Yes, we have those. Now we have component equations which again directly link force to some kind of acceleration, some kind of velocity, some kind of displacement. So here for a mass, your mass is going to experience your mass times acceleration, okay? This is also known as an inertial force. And the equation for that is just going to be your force is equal to, so here force on component A is going to be equal to the mass of component A multiplied by the acceleration of component A. And here, because there's only two vectors, your force and your acceleration will both be in the same direction, okay? Since we're only dealing with 1D linear motion for right now, there's only a positive and a negative direction. So pretty simple there. Okay, second type of component that we're going to deal with is something called a damper. Okay, this is also known as a resistive force. Okay, basically what a damper is, it may not be something you've seen in physics before, might have briefly talked about it in physics. We might have briefly talked about this in dynamics. I don't remember. But what you have is, typically you'll have some kind of a tube, and in this tube you'll have a plunger, and this plunger will consist of some kind of, it kind of looks like a potato masher, because you got little holes in it like this that are all over, and this tube then is filled with some kind of fluid. So as this potato masher object, this damper, travels through this tube, you experience a lot of fluid resistance to motion, okay? That's kind of what a damper does, is there's a fluid resistance to movement. Now that does incur a kind of force. This is similar to what we would consider a lot of friction to be. In mechanical engineering, there's going to be bearing resistance. Bearings are oftentimes lubricated, and so while yes, it's modeled like this, bearing resistance can actually be considered something like this too. We'll get into that later. But this is what a damper is. It is friction. Okay, and usually these dampers are, they use friction as a way of dissipating heat. So friction forces, they just result in heat. Yes, smooshing this thing through this sloshy water, that's just going to produce some amount of heat over time. And all the energy that gets put into there is going to eventually become heat. So for this damper, the force relationship is given as, I should have written this a little differently. I give the subscript A because it's all on one component, but I like to label things according to what type of force they are, what type of acceleration they are. Here, this is Fm for component A. So Fm A is equal to A. There we go. Mass of component A multiplied by the acceleration of component A. So here the damper is, there's a lot of different subscripts you can use. I typically just like using FD. A, because it's on component A, is equal to, you'll have some damping coefficient, which is oftentimes represented as a B. Most of the time in this class, this is going to be a constant value. Make things easier for you. If that changes, I'll let you know. We'll work a problem. And then this is actually related to the velocity of component A. So here, if this plunger is traveling at 5 meters per second, you can expect the force that is exerted by the fluid on the plunger to be linearly correlated with the speed of that plunger traveling through the tube. okay? Damper. And then the last component that we have is a spring, okay? A spring is it's considered to be a capacitive force because it stores energy through compression, okay? Compressing a spring, you're going to have some, it ends up coming down to a more microscopic level and being stored in strain energy as the wire actually twists inside of the spring. Spring mechanics are interesting. For a mechanical engineer, maybe not to anybody else. But here it stores energy in a capacitive force. And then this just uses Hooke's law, where F, and then for this course, I guess I'm going to use, I think we can use FS. Okay, FSA, so on component A, is going to be equal to your spring constant K multiplied by the delta displacement XA. I'm not sure if that shows up on camera. Let me zoom out. Okay, now it shows up on camera. Woo! Camera. It's at the bottom of the board. Should probably make sure that this is actually showing up. No, it's... There we go, we got it. Okay, so those are our three components. Component, our one system equation. We do have some helper equations too in this one. Unlike the electronic systems, we don't really have the same types of helper equations. Our helper equations were that we just had two different types of system equations. So our helper equations we can technically consider to be system equations, just because that's how a lot of this works. But you have all of your relationships between your motion. You have in Cartesian, which we may or may not be working only in Cartesian. We may be working in other styles, you know, your tangential and normal components, your radial and transverse components. We may be working in those too. So just make sure to keep your eyes out in case something like that happens, and come ask me questions if something pops up. You don't remember how it is. I might direct you to your dynamics notes, but you may not. But in Cartesian, what you have is the time derivative of your displacement is equal to your velocity, and the time derivative of your velocity is equal to your acceleration. Okay? Oftentimes, this is, in this class, going to be designated by an x dot. And then here, acceleration being a derivative of x dot is going to be x dot dot, or double dot, okay? The dot signifies that this is a time derivative. That is d dt, okay? So that's all the dot means. If you're familiar with seeing the dot, it'll be a little bit easier for you just understanding the course. For me, dots didn't really click for me in school. They clicked for me more in grad school. And then it became a lot easier. But I also didn't have people who just sat down and said, okay, if I see a dot, it's always ddt, always time derivative, okay? Time rate of change. The dot is very special because a time derivative with respect to time tends to be pretty special. Time matters a lot. All right, so we have all of these equations that we can use. Note, it doesn't apply for radial or normal coordinates, and that includes transverse and tangential components too. Okay, so these do not work here. You'd have to look at the specific formulas for that. Still not sure if we're going to be using those other coordinates. While they are valuable, they can be kind of a pain in the butt, and we can do most everything in Cartesian because it's just simpler. Cartesian gives us nice perpendicular lines to work with. Everybody likes simple. Okay, so these are all the equations we're going to be working with on this particular system. Now, one of my favorite examples to use when we're talking about linear motion is to actually go in and model a chair. So in electronic systems, your system configurations were given to you by, you would have, here's a circuit diagram, here's the model that we're trying to implement. And in electronics, it's simple enough to be able to operate because every single component can be represented by a single component that shows up in your circuit diagram. In the real world, it gets a little bit more complicated because let's say I'm going to be modeling a chair, okay? So, example, chair. For this example, it's going to be a chair much like the ones that we have in our classroom. Oh man, I may not be an artist, but this is probably the greatest drawing I've ever had in my life. Look at that chair. Hold on, I gotta update my resume with this now. Artist. Okay. Yes! It's finally happened. Now I can stop using my fallback career of a comedian and have my fallback career of an artist. As the camera gets blurry, and you will never see anything else that I draw ever again. Terrible. Anyway, so here's our chair, okay? Now when we sit in this chair, sit. When we sit in this chair, what's gonna happen is the chair is going to compress. Wow, not like that. Oh, my artist career is falling apart as we speak. Granted, I'm trying to draw sideways. Yep. Change my resume. Remove artist. Well, at least I still have the comedian fallback career. When I get done with this, I'm gonna have to read a book on how to be funny. Okay, so you'll notice that this chair actually goes down. It compresses as you sit on this. And this is gonna be something that you test too. Sit in your chair, it compresses, okay? Even these types of chairs, which are rather rigid, there is a cushion on it that compresses. If it did not compress, you would definitely feel some pain as you try to sit down on that, because it's just, yeah, it's like sitting on a hard structure. Sit gingerly, because your butt's going to be the one compressing. Also, hi Logan. Thanks for tuning in. Okay, so this is compressing. Now, in the compressing process, we have to take a number of things into consideration. How does this actually move? When I sit on this, what's going on here? Okay, so we're going to do a little bit of an analysis on this. And the first thing that we're going to have to do is we're going to have to model it. Now this is very different from what we were doing in circuits. In circuits, you were handed a model and told, here you go, take this, run with it, figure something out. Start math, go. And then you went. Here, we're going to start with modeling the chair, okay? So what does that mean? Well, it means we got to break it down into our components. I will be blunt with you. Systems and controls is one of the most challenging areas of any design process. This can be considered to be one of the highest level features of any design aspect. because it really does incorporate just about everything into it. And it's a high-level look at every one of the subjects you've taken so far. So for us to do this, you will be able to propose about 5 different models or 500 different models, and maybe 400 of them are bad. Some of them may give you reasonable results. Some of them may be really off or may only be applicable in certain situations. And yes, you can just keep doing that. My battery's running out. I'm going to keep talking while I replace this. But we have to be cognizant of how the performance of our model goes, but that still starts with us identifying a model. And so typically what happens is you're going to have somebody who comes up with a model, proposes a model, implements a model, sets up the model, measures the model relative to the actual performance of the system, sees if the model actually, works relative to, like, so if I build a model of this chair and then I build the chair and the chair model and the chair behavior are very different, my model doesn't work. My model is broken. So I have to go to a different model, okay? Or figure out what's wrong with my model. And that's the process of design in this regard. But once you have a model, then you just run the math. Later on in this semester, we're going to get into a process of, once I have the equations, how do I make the computer do all the math for me? Because I'm much more into that aspect. I do not like doing a lot of math by hand because I can be very errant when I do that. Okay. There, we have our audio feedback. Battery replaced. Bam! I didn't say any words while that was off. Yeah. This blurring in and out is driving me nuts. I can't imagine how this is driving you nuts too. So, hopefully we don't have to do this very often. Also, my office is heating up substantially. I'm gonna start dying soon. So, only a few more minutes left on this video. So what are we gonna do to propose this model? We're gonna come up with a very simple one. This model is going to be chair, seat. We have both a spring, which I guess I should draw it like a spring. Also, by the way, same type of symbol used for an inductor, although I guess an inductor looks more like this, whereas a spring tends to be a little bit more centrally located. But this is a spring in linear, and a damper is drawn like this. Okay, so here's your spring. And in this type of system, the fluid that's going to actually be in the damper tube is going to be air. So you'll have some type of movement inside of that air that creates viscous friction so that, see if moving my light closer prevents this thing from being so friggin' blurry all the time. So far, so good. Okay, and then we'll mount this directly to ground. Yes, it can roll. No, I don't care about rolling right now. Okay, so there's where we're at. This is going to be the model we use at first to evaluate our system. Okay, and now what we're doing when we sit on this is we are applying a force. But we're also doing one other thing, and that is we're applying a force and adding a mass. So when we do it, we're changing the system from just simply a chair seat at this configuration to a chair seat and a body. Okay? and both of them fairly rigidly connected. Your butt hits the seat and they merge together and you're stuck with it for the rest of your life. Enjoy sitting. Enjoy sleeping too. Hopefully you can sleep while in a chair on your bed. Yeah, that's weird. Anyways, so we've got the spring, we've got the damper, we have our model. This is what's going to be our model. Prior to t equals 0, which here's our switching event. We're going to have the body absent from the system. Okay? Woo! Now, because these are real components too, we are going to have to add in one more force that wasn't in our components equations and our system equations. We're going to have to include gravity into this, okay? Now in this system, this is operating, we'll say that this is the positive x direction, where the floor is 0, okay? Gravity actually acts in the x direction. And for that reason, because gravity is going to be a major player in the operation of this feature, like, you know, if we didn't have gravity, you couldn't sit in your chair. You would just perform a squatting feature above the chair. So the chair's necessary function comes from gravity, okay? So here we know we're going to have to include gravity because we know gravity has an impact on the system, okay? So knowing that, we'll have to also include an FG value inside of our masses. We'll get to it. Now, when it comes to our one system equation that we have for this, plus the helper equations that we have, we're going to start with our one system equation because it's always going to include our forcing function. Here, our forcing function is the presence of the body mass. So before we really get into something, let's go ahead and identify what steady state 1 behavior is for this system, okay? So here, let's M chair. We'll say that you know, it's just the seat of the chair. We'll say that this is going to be 1 pound, okay? Yes, I'm using imperial units. No, you can shut your face because we're going to keep using imperial system because America, heck yeah. Flag waving. We have also got M body. Okay, and this one, we'll have it be equal to 150 pounds, okay? Just regular human person with regular human body. Okay, so there's 2 of our features. We also have the K value, which is our spring constant for our chair spring. K is going to be equal to, we will say 50 pounds per inch. Okay, so you load this thing with 150 pounds, you would expect this to deflect 3 inches. In actual chair values, it's closer to maybe 2, so this would be like 75 pounds per inch, maybe. I guess we should, well, let's do 75. That might actually be closer to 100, but it's whatever. And then we'll add our B value, which is our damping coefficient, and we'll have that one equal to 20 pound, and the units on this one is pound seconds per inch. Okay. Why is it that way? Yes, thanks science. This is because this multiplied by a velocity is going to be equal to a force. Okay, you'll get pounds out of that. All right, so now that we have our values, let's go ahead and run some calculations. So, steady state 1. Okay, at steady state number 1, this is going to be prior to t equals 0. The body is going to be absent from the system. We just have the chair seat sitting on top of a spring and damper system. Okay, how much is the spring compressed? How much force is the damper exerting? Well, let's do a quick force analysis here. So here we have we only use our system equations on our inertial bodies here. Okay, kind of one of the interesting things about kinematic systems is we only care about this. We're treating this as if it's massless. We're treating this as if it's massless. It only exists to exert a force. All of the actual mass is contained up there. Okay, so we have our M chair. On M chair is exerted FG chair. Okay, that's coming downward. We have our upward motion, FS, which is our spring, and over here FD, which is our damper. Okay, and then we'll also have an inertial force. Typically what you do for an inertial force is we're establishing X positive in the upward direction. What you'll do for an inertial force is you will actually make the inertial force always point in the negative direction. Do not ask me why, but that's how you end up with your F equals ma, is because this inertial force is a negative over here, and it's always a negative. So you're gonna pull it out, move it to the other side, and have it be a positive. It's just always considered negative, okay? So this will be M, we'll go ahead and call this F M chair. Okay, nice. We got FG chair, FM chair, FS, and FD. And the total sum of forces, as we've said, our system equation, sum of the forces is equal to 0. Here, all of the forces are acting in one axis. They're all acting in the x-axis, up and down. So we can just write out our 4 forces. We have FS plus FD minus FG chair minus FM chair is equal to 0. Okay? Now, in this steady state, we go over there, it doesn't look like the chair is moving. So what we're going to assume our initial conditions are during steady state are that velocity is equal to 0, acceleration is equal to 0. It's not moving. It is at some rigid fixed displacement, not moving, present on the floor. Okay? Because of this, we know that when we start writing out these equations, this one's going to go away, this one's going to go away, and you're left with only those two. So we'll go ahead and write out those equations. I'm going to put it right here. I wish I had like twice as big of a whiteboard. Oh well, dreaming. All right, so let's go ahead and write out this equation, and we'll write out what each of the components of this equation are. So Fs is K delta X plus, and I'm going to say X chair specifically, because that chair value, we're only looking at the displacement of the chair seat. We have FD, which is B X dot chair, because again, only looking at the chair seat. Chair, that's why it's this part of our model, is this very much pertains to what we're dealing with. Minus FG chair is M chair multiplied by a gravitational constant. Here, M chair is 1 pound. That is, this ends up actually equaling FG chair, because that's a force already. This is equal to FG body. So, kind of misleading to call it a mass, because it's actually a force. Good job, me. So I might as well just write that as FG chair, because we know what that value is. minus m x double dot chair equals 0. Now again, the time derivative, the chair's not moving in either direction, so we know this one's going to go to 0 because it's not accelerating. This one's also going to go to 0. That means I don't have to calculate what the mass is for that one yet. And we're left with k delta x chair minus fg chair equals 0. Okay, basically what that means is that this chair is going to have some displacement relative to the original length of that spring that's unloaded, and that is the delta x. And this value multiplied by the spring constant is going to be equal to how much the chair actually weighs. So if we were to take the chair seat out, the chair would extend just a small amount. Okay, so this one is 75 pounds per inch. This one here is 1 pound. So we have, just going to go ahead and set it on both sides. K delta x chair is equal to fg chair. Okay, and then we'll divide both sides by k, so delta x chair is equal to fg chair divided by k. So delta here signifies the change in x value. So this is the change in x relative to the unloaded spring value. Change in x value is equal to the weight of the chair divided by k, which is 1 over 75, which I'm not going to look up that number because that's pretty small. Okay, and units on that are going to be inches. Okay, so this is going to deflect 1/75 of an inch just under the weight of the chair itself. Okay, so that's good. We know that we are 1/75 under whatever the natural unloaded spring length is. So I'm going to call that x unloaded for the spring length that of the unloaded spring where there is no force in the spring and it's unloaded. We'll call that x unloaded, and we'll set that one equal to, let's see, about 18 inches. Okay, so if I were to take the seat off of this chair, it would be 17 75ths of an inch above the ground. Yay, nice. All right, so all of this was intended to give us an analytical position by which we can start now to understand how this chair moves. This is the position of the chair right now. It is 1/75 under the uncompressed, unloaded chair spring length. Okay. Now, once you sit your butt on it, it causes the chair seat to drop. Okay, because you are exerting a load based on your gravity, and that is, it's compressing the spring element in the chair. Okay, how much do you compress it, and what is the shape of that curve? Well, again, we have these three components. Once you sit your body on the chair seat, your new weight is now 151 pounds. Okay, the moment you put it on there, your body, the chair, they become one. You know, all of those Zen things with their we are one with each other. I am one with the chair seat. Okay, and that's how life is at this point. It's a unification. Your butt married that seat, and now you have to deal with the ramifications. 6 kids and oh, well, wait, no, wrong one. Sorry. They're stuck together. Okay, there's not a spring in between them. There's not a damper in between them. They move together as one. The way that you know that they're stuck together is the displacement of the chair seat equal to the displacement of the individual themselves. Okay, is the displacement of the chair equal to the displacement of the body? If this is true, then that also means that V chair is equal to V body, meaning there is not going to be a velocity difference between the two. Okay, and A chair is equal to a body. Basically, every derivative of displacement will be the same in both cases. If this is true, then all of these are also true. Now, this is true. When you sit on that chair, you move with the seat. You become the forcing function. Okay? So, because they are the same, we can treat them as if they are now one solid body. And that's what we're going to do. Our modeling becomes a little bit easier because we don't have to treat them as two individual bodies. Okay, yes, you could have your body displacement be measured at your bone structure. And yes, you got a little bit of, you got some padding down there that's going to deform as you sit down. And so, yes, your body skeleton is going to shift relative to the chair seat as you sit on it. Okay? Yes, that's bound to happen. You really want to model some relationship between these two. That would be how it is how does your body react to different models of a chair? We are not going that deep in right now. I told you there's 500 different models. That's one of them. Okay? And you can get way more complex than just that. We're doing the simplest model possible. Assuming you are yourself a rigid body, when you sit on the seat, you are all one rigid body. Okay, so now, after t equals 0, this situation comes up. So after t equals 0, you have body plus chair acting as one unit. And you now have your forces. You have your spring force, you have your damper force, you have your gravitational force, which is body plus chair, and you also have, because this is the positive x direction relative to the ground, this is the inertial force. Okay, which I'm just writing as x double dot chair. Okay, we're going to use all the chair values because, as I established earlier, our assumption here is that x body equals x chair at all times t. Okay, so this is the model that we have now after t equals 0. We have an initial condition, and that is that the chair seat is currently located at 17 and 74/75ths of an inch above the floor. That's our initial condition. Okay. Okay, so initial conditions. This is one of them. We know our initial position. Okay, the other one is, as we've already mentioned, this chair is not moving. So we know this is one. Second one is that x dot at 0 is equal to 0. Both of those have to be true. We're going to be dealing with a second order differential equation here. Doing this again? Yes, we're doing this again. All right, so with that set up, let's go ahead and do our math for this one, okay? It's the same equation. Okay, once again, sum of forces equals 0. The sum of all of our forces are going to be equal to Fs plus Fd minus Fm minus Fg. Yes, I'm not writing out Fm chair, Fg chair, because I'm assuming that they're all one body at this point. We'll have to take M into consideration for being now 151 pounds. And we'll have to take Fg into consideration for now being the sum of both of these. Okay, so rather than write out these two plus each other, these two plus each other, I'm just lumping them together. Okay, this is equal to 0. Same exact equation as we were dealing with earlier. The only difference is now these are non-zero entities because this is moving. Okay, we're going to have a transient portion. We're going to have a particular solution. All of the things that we just dealt with, we're doing it again. Just this time in kinematics. All right, so fun fact. Where's our forcing function here? Forcing function is the outside power that's being exerted to the system that is causing the change in the system. Here, the only change in the system is that Fg and Fm both changed. Fm wasn't a factor in the original position. Fg was. Okay, Fg changes. Because Fg changes, we now have that as part of the forcing function. In our case, Fg is always going to serve as a part of the forcing function for our equations. So I'm going to set this as forcing function on one side, every other piece on the other side. Okay, start off with that. We have Fg is equal to Fs minus, Fs plus Fd minus Fm. Okay, so starting off with our equation, there we go. Next step, we got to find what we're trying to solve for. Here, what we're trying to solve for is the relationship between the force and the displacement. We want to know how high the seat is, and we want to know what the trajectory of the person as they sit down are. Because that'll also tell us, like, what's the maximum acceleration you experience. You don't want to experience a lot of acceleration when you sit on a chair, because that's painful. But then again, you also don't want to experience too much displacement, because then you're, sitting in a beanbag chair where you're just like, and you like fall through the floor. So, we as designers, we have to take these things into consideration. What is an acceptable level of acceleration for this individual, given a rational, normal sitting condition where you just kind of ease into the chair? Okay? And here, because we're assuming that there's no velocity, you are not plopping on the chair. You are locating your butt onto the seat and then releasing the force from your legs, allowing gravity to sink you into the chair. Okay? Which even then, that's not quite realistic, because in a normal seating situation, some of that force is carried by your legs to prevent you from, experiencing the maximum acceleration caused by sitting down. So this is already kind of an extreme situation, because we could have another force in here that represents the force of the legs upward. But I'm not doing that because it makes the problem slightly harder. We'll talk about that later. All right, so we have this, okay? We have our one component here, and all of these can be defined by x values, the displacement. So we'll go ahead and just plug in our component equations. Fg, we know that that is 151 pounds, but I'm going to leave it as Fg. Okay, is equal to Fs. Fs is your force, your spring. This is K times delta X plus Fd. This is your B times X dot minus Fm, which is your M total, multiplied by X double dot. Okay, so this is a little simpler to get to the final equation for this. We're gonna make things harder because that's what we do in this world later on, not today. But the last step of what I did to get this to be a constitutive equation is here. This is the highest order differential. We're going to divide this whole thing by m. So we have Fg over m is equal to k, is equal to, oh, we're going to divide it by negative m. So this will be a minus sign over here. And this is x double dot minus b over m x dot minus k over m delta x. Okay? And this is now going to be our constitutive equation. You know it's a constitutive equation because there's no coefficient right here. So how do we solve this? Well, what we introduced in class was the idea of alpha and omega naught squared. Okay? And we can use that to solve the problem. We're going to be doing the same thing here. We're going to take this equation and we're going to put it in the form of big F of t, which is your forcing function, is equal to x double dot plus 2 alpha x dot plus omega naught squared delta x. Okay, and yes, we've got a weird minus sign in there. That's gonna make things a little interesting. But that's where we're at right now. Okay, everything is set up, ready for us to really figure out what's going on here. Okay, so now we just set these equal to each other. We know f of t is equal to negative fg over m. Okay, that makes sense because it's acting in the negative x direction. Alpha is equal to negative b over 2m. Okay, kind of important. And we know omega naught is equal to, this is where we have to include an I value, square root of k over m, and then I'm going to go ahead and drop an I in there because that's what happens when you take the square root of a negative number. Not good. The I is eventually just going to go away. Okay, so when we go to calculate our zeta is equal to alpha over omega naught. Okay, so we're going to do our calculations here. What is b over 2m? Well, we're going to need to calculate what m is. So m total equals 151 pounds. Okay, and then we have to divide that by our gravitational constant, 32.2 pounds per foot. Okay, now the problem with this is that this is in pounds per feet. And then basically we have to multiply this by 12 inches per foot. Okay, if you do your unit analysis, this comes out to being what? Don't have my calculator on me. I got my phone. So this comes out to be 151 divided by 32.2 times 12. This is equal to 56.27. And I don't really know what the unit is on this. It's like, it's a pound. So this is foot per second squared. So this is a pound inch. It's a foot per second, so it's a pound inch per second. We're going to go with that. Not a standard unit. Otherwise, we would have to convert all of this to feet. Yay, imperial system. Actually, I really like the imperial system, but I'm also a nerd, so this doesn't bother me. So we have 56.27. That'll allow us to plug this into our m values. So we'll just go ahead and calculate that. Alpha here is going to be equal to b over m. So that is 20 divided by 2 times 56.27. Here we're going to take the absolute value when we do this calculation. 20 divided by 2 times 56.27. That's going to be equal to 0.1777 for our omega naught value, as the square root of k is 75 divided by m, which is 56.27. And that is equal to 1.1545. Okay, so when we calculate zeta, there's an I on there, but when we calculate zeta, this is going to be equal to 0.1777 divided by 1.1545, which is equal to 0.1539. This is less than 1. This is an underdamped system. What you're going to have happen when you sit in your chair is you're going to oscillate. Okay, and that's actually what kind of happens. You bounce in it. A good chair will have a strong enough damper that It won't do that, but apparently this is not a good enough chair with the values that I picked. This probably should be closer to 2,000 pounds, but yeah, yeah, we're good. If you just increased the B value, that would change your zeta significantly. All it needs to be is like, it just needs to go from 20 to 200, and then it's more critically damped. Should be nicer, but you know, whatever. All right, so that's where we're sitting. We're gonna have an underdamped system. I'm gonna go ahead and leave it off right there. We'll pick this up in our next class. So yeah, I will see you then.